Welcome to lecture 17 of the CS4423 networks. My name is Götz Pfeiffer and this video is about the configuration model. So where are we? We've been looking at random networks on the one hand and then a bit on real-world networks, and we've been identifying a couple of properties that real networks do have, like short paths and high clustering, and that are not really reflected in the random graphs. So the random graphs, they do have short paths but not high clustering, and the latest phenomenon that we want to catch up on is the power law that governs the degree distribution of certain real-world networks, and that's something that has been observed in biological networks, in citation networks, in other document networks like the World Wide Web. And on the way, we've built this Watts-Strogatz model, random graphs that are supposed to simulate small worlds, but there again they don't have a power law degree distribution. So that's what we'll try and do now before the course comes to an end, to generate, again as randomly as we can, models of networks that do display this power law in their degree distribution. Last time we saw a process, a natural process that yields a power law by randomly increasing quantities or inventing new ones, and thereby having the rich become richer. And this phenomenon expresses itself as a power law. So from there we sort of know how we could make a degree distribution that follows a power law. We're going to use such a power law degree distribution now to fit a random network to it, a network that will have a prescribed degree sequence. This might be surprising, amazing, but there's a simple trick behind this that is used in this configuration model to start from a prescribed degree sequence, which is the flattened out version of the degree distribution, and generate a network that has exactly this degree sequence and consequently the given degree distribution. That's the approach we'll try here, and in the next and final lecture we'll see another different, maybe more dynamic approach to this, to address the same question. So for this I'll include a couple of libraries. We'll draw on various functions in Python's random library. We maybe should have last time already used the counter objects from the collections library, and then to make things efficient and have them drawn nicely, we include NumPy and matplotlib as well, and as usual the networks library. So with that in place, let's get started. Now, how to generate a random graph that has a prescribed degree sequence. The idea is the following. In this configuration model, you start with a degree sequence, that is a sequence of integers di, the degrees, di is the degree of the ith vertex in the vertex set X, such that now it is a degree sequence. We know that the sum of the degrees is an even number. That's Euler's handshake lemma. So this sum must be even 2 times m, 2 times the number of edges in the network. Then here's the simple idea. Since each, how do you put this? Each edge, each of the m edges, obviously contributes to the degrees of 2 nodes. It's two endpoints. We regard each di in the sequence here as di many half edges, stobs if you want, that are attached to the node I. And then being a half edge, it needs to join up with another half edge that's floating around in order to form a full edge between node I and that other node. So each di in the degree sequence gives di many, say, just copies of the node I. And then we compute a random matching between the entries in that list of stobs and take these matches as the edges of the graph. And there's the random element, the random matching. It probably helps to see this in action in an example. So let's take as a small vertex set the 5 vertices 0, 1, 2, 3, 4, and let's prescribe a degree sequence 3, 2, 1, 1, 1. And node 0 we want to have degree 3, node 1 we want to have to degree 2, and nodes 2, 3 and 4 we want to have degree 1. Following the recipe that's listed here above under the name of configuration model, we take this degree sequence to turn it into a list of stobs consisting of 3, which is the D0, 3 entries 0, followed by D1 entries 1, so this 2 here, the multiplicity of the 2 node turns into 2 entries 1 in the list, followed by 1 entry 2, 3 and 4 each. And that's our list of stobs or half edges, which are now supposed to join up with each of them with another half edge in a random fashion. And one way to achieve this is to randomly shuffle your list of stobs, like you shuffle a deck of cards. Bring this in a random order and then cut it in half. So take this one line thing and make 2 lines out of it, and then the columns of this 2 line arrangement are the matches. So this sequence 0, 2, 3, 0, 1, 0, 4, 1 becomes 2 lines 0, 2, 3, 0, 1, 0, 4, 1. And if we read this column by column, we get an edge between 0 and 1, an edge between 2 and 0, an edge between 3 and 4, and an edge between 0 and 1. That's 4 edges, half as many as we have here in the sum of the DIs, which was 8. That's 2m, so we get 4 edges. And now we also see some of the problems with this approach, as in the edge 0, 1 here is taken twice. Do we want that? Well, let's not be disturbed by such things for the moment. Let's see, can we teach Python to do this and then maybe improve on it. So on the Python side, we start with a list degrees. That's the list 3, 2, 1, 1, 1, corresponding to the degrees of the nodes 0, 1, 2, 3, 4. Starting as you do in Python at 0, and correspondingly we have called our nodes here 0, 1, 2, 3, 4. And then as the next step, we want to take this entry 3 in position 0 of the degrees list and turn it into 3 entries 0 in the list of stops, followed by 2 entries 1, followed by 1 entry 2, 3 and 4. And one way to do this is to use Python's list arithmetic. You might remember that the star operator applied to a number and a list makes repetitions of that same list. And also list arithmetic. This is attaching meaning to plus and times and maybe other operations to working with lists. And a number m times a list A stands for m repetitions of the list A. And the sum of two lists in Python is taken as the concatenation of those two lists as a concept. So we can take each entry in our degrees list. We can take the ith entry in our degrees list as multiplicity and turn it into that many copies of a list consisting of the entry I only by forming this product. Degrees at I times the list I. What did I do now? We do this for all, and we do this for all the positions in the list degrees. Why is it I don't like this? Let's try. Let's try. I've been told you shouldn't do this. Range of length of degrees. You should instead enumerate your degrees list, and the enumeration of the degrees list results in pairs consisting of the position and the value in that position. And then I can just take d copies, which is the value in that position of the list I. That's a bit cleaner, isn't it? And it results in the same thing. That's the process I've described before, now implemented in Python. Almost. Now I get separate lists, one list for each entry in the degrees list, and I'd rather have them all in one list. But yeah, adding lists is the same as concatenation. So if I ask for the sum of these lists, starting with the empty list as the initial sum, I get all of these entries as a single list. 0, 0, 0, 1, 1, 2, 3, 4, just like we had it before. Okay, and then we can turn this into a Python function by wrapping this all up into enumerate I, d, enumerate I, and I pass the empty list here as in case there's nothing to add up, and this will return the empty list. I call this stobs list. I call this function stobs list because it takes a list as input and it produces this stobs as output. And applied to our list of degrees, it gives us the sequence of numbers, as expected. Next thing then is shuffling this list into a random order. There's a nice procedure named in honor of Don Knuth, who has invented lots of things there, or made them more efficient. And it's mentioned on the Wikipedia page on random permutations. There's a simple algorithm that you can write yourself in the absence of any permutations as explicit data structure or objects. For random shuffling of a list A in place by simply looping over the positions K of the entries in the list and then swapping the entry at position K with the entry at a randomly chosen position J greater or equal K, allowing for the possibility that J is equal to K and the swap has no visible effect. The promise with this algorithm is that this simple list of instructions produces a uniform outcome. Each permutation of the entries is equally likely, and it's implemented in a few lines here, as I call it the Knuth shuffle of a list A, setting L to the length of the given list. Then we loop with K over the positions of the list. That's the range of L. In the body of that loop, we choose J to be a random integer between K and L, including the K, excluding the L, and then we swap A at position J and A at position K, regardless of whether J and K are equal or not. So we've applied to the list 1 to 3, a random shuffling in place gives 3 to 1. And one can quickly test whether this really gives a uniformly random outcome by applying the procedure a large number of times to a short list and keeping track of the outcomes. Let's shuffle this list 1 to 3, say 10,000 times. And I count in this shuffles dictionary how often each of the, how many 3 factorial, that's 6 different permutations of 1 to 3 occurs. And there they are, and they all occur about 1,700 times. Which is 1,700 is roughly 1/6 of 10,000, isn't it? So within the within the error bounds, this is a uniformly random outcome. Each possible outcome is approximately equally likely. Actually, as often, Python has such a shuffle function which does exactly that in its random module. So we can call on random.shuffle for the same effect. And we can apply the same test to the random shuffle function, shuffling 1 to 3, 10,000 times, counting the outcomes, and see again that each of the 6 outcomes is equally likely. So now with that we're confident that either shuffling procedure will give us a random shuffle of the stops. So like this, for example. That's our given list of stops shuffled in a random order. To match this up in pairs, we cut the list in halves. So we take m to be half of the length of the list, and then make 2, and then cut the list in halves up to m and from m onwards. And one way to transpose this at the Python level, wait, I need the m, is to zip the star of the edges. That's effectively the transpose of this 2x4 list into a 4x2 list, and that gives a list of edges in our random graph. 4 of them, and there's a picture of the graph, leaving one unconnected. And there you see again one of the drawbacks of this approach. 1, 1 isn't really an edge in our sense of simple graph. An edge in a simple graph connects two distinct nodes. And of course this can happen as the outcome of this procedure. Let's not worry too much about this for the moment. Let's take what we have, wrap it up as a Python function configuration, which takes a list of degrees and then turns those degrees into stops, randomly shuffles the stops, turns the stops into edges, and then constructs a graph on the basis of these edges. And that's a Python function configuration in which we can pass our list of degrees, and then this will take the same list of degrees and draw and construct a different graph. This one now only has 3 edges, presumably due to duplications in the pairs, and that's the resulting graph. As I said, I don't want to worry too much about these deficiencies. Something will come out for bigger numbers, and that's where we go now. Let's try and feed in the power law degree distribution. And for that we start with the power law using the algorithm from last time, but maybe in a way that it generates the stops directly rather than the degrees, which are then distributed according to a power law. And that makes it slightly shorter and maybe conceptually easier for what follows. So similar to last time's algorithm, I define a new one, call it power stops. It takes as input an m and a probability p, which I guess we'll take for 1/2 most of the time. And rather than distributing m things with the application in mind, we make sure that we get an even number at the end of the day. So we distribute 2 times m things in this rich get richer fashion as before. But 2 times m. So this is the same procedure as last time. This time I'll set a counter L to 0, memorizing the name or the number of the thing that was entered last into the list. So we start at 0, and we start with a list X that has exactly that one entry, 0 only as its first entry, and then for the remaining 2m-1 things to be put into the list, and we repeat this list of commands 2m-1 times. We flip our coin, and when it's heads, if the random number generated here is smaller than 1/2, we increase this L counter by 1 and then add a new number L to the end of the list. And if that number turns out to be bigger than 1/2, we pick as k something that's in the list already. Now some of the things in the list will occur more frequently than others, and therefore now have a better chance of being picked again. And same as last time, the chance of this number k to be picked at this point is proportional to the number of occurrences of k in the list already. And then we append this k to the list x. And at the end we return this list x We don't have to do this. We don't do the counting. Don't do the counting here. That's my function power stops, and if I apply this to, as I said, I take p to be 1/2. Let's make this reasonably large and pass and take 200 as parameter m. That'll then create 400 stobs for 200 400 stobs. 400 stobs is 400 stobs for exactly 200 edges, isn't it? Edges on approximately 200 nodes. The entries in the X list that is generated here are node names, and if every second time, or with probability 1/2, we create a new name, then we'll end up with approximately m many different names in the list. Well, let's see. So power stops of 200 with probability 0.5 gives, okay, a list of stobs, node names with repetitions. And okay, this is a bit difficult to read, but you see that 1 here occurs frequently at the beginning and therefore has a good chance of being picked again, like here, here twice, and so on. That's a list of 200 node names with repetitions. Here it serves as stobs, and since they're added in order, I can see there's the last one is 189, so there's 190 nodes in this game in total. What? I've started it again, no? And now I have what? Now I have 206 nodes, and it's not 1 that's frequent, it's 0 that's frequent. Okay, let's work with this list then. Then that's where the Python counter in the collections library comes in handy, because the counter counts how often applied to a list. It counts how often each item in the list occurs, and it returns this count in the form of a dictionary, very much like the our power law function from last time did it. So let's see what's the result of this. Now we get a list, we get a report on, well, in this context, on each node name between 0 and 206, reporting how often this node name occurs as a stob in the list of all stobs. And you see that later nodes here occur. It's not later. No, there's this funny property of this counter being printed out. It seems to be printed out in an order that respects the values of the keys, or actually in decreasing value of the key. That's funny. So all the values 1 here come in the end. Down here everything has value 1, and the high values are at the beginning. And you see here that node 0 is mentioned 55 times, and the next one up is node 9, mentioned 10 times. That's a factor 5.5 less. And that's your power law in action. Node 11 is mentioned 8 times, and then it decreases drastically with lots of ones there, and at the end. So that's your power law in action. That's the counter. and so that the power law is concerned not with the degrees. So these are the degrees of the nodes, and the power law is not concerned with the degrees themselves, but with the degree distribution or the frequency of individual degrees appearing. So applying the counter again, applying another counter to the list of values that we find in this counter will get us maybe not the degree distribution, but these counts, these degree counts, nk. How many nodes have exactly degree k? Now we get that from applying the counter to the node degree list, to the values in that dictionary. Let's call this nk, and then we get a report that node degree 1 appears 140 times, node degree 2 appears 31 times, and so on. And the feature of the power law is that high degrees do appear. Not often, but they do appear in, and they're not negligible because they do appear, and they're high degrees. So degree 51, it says here, appears. Degree 10 and degree 8, and what 55 is really a big entry, non-negligible entry in this list. Let's check graphically whether these numbers do represent a power law. They really should by construction, and that's the algorithm from last time, which we used to produce such a power law distribution. So I follow similar steps as before. I take these counters, I take the values and I take the full list. I take the values together with the counters. I take the degrees k, which are the keys here, together with their values nk, and turn them into a NumPy array. That's the same information as before. It's a single array which I call x1 because it consists of the x values and the y values at the same time, and it says that 55 occurs once, 1 occurs 140 times, and so on. And then I can use these values and throw them into a log plot as provided by the matplotlib. And well, now you have to imagine a straight line of slope, minus 3. One thing one can see here is that we started with 200. We started with 200. We started with 400 stobs for 200 edges. And then applied a counter to that and another counter to that. And at the end of the day, you only have a handful of values to witness the power law, which is one of the aspects that make it difficult to actually verify a power law distribution. So I guess you have to be kind of generous to see the straight line here that would verify the power law. But it's sort of, now you have these 3 dots here lying at the bottom. I'll do this again. I'll do this once more. Maybe we get a different picture. So starting here, I generate another 400 stobs, apply the counter to it, apply the counter to that, turn this into x and y values and plot it as a log plot, and you get something of a similar nature, just to illustrate the kind of flexibility that needs to be applied here. This is another picture of the same power law. Okay, yeah, and then let's, in the list K we had the node degrees. Let's use these node degrees and feed them into our configuration program to make an actual graph that displays this power law degree distribution. And you see, okay, you see many small components. You see a big component in the middle, and there's so many nodes that apart from that you see very little structure. Maybe it's helpful to just look at the giant component. Here the giant component has 144 of the roughly 200 nodes, so it is really big, but then it's connected. So that's the nodes in the connected components. Let's just go for the largest one, the maximal. If we sort the connected components of G by length and then take the maximum of that list and look at the subgraph of G on that node set, call it C for the giant component. Let's plot that. And there some structure emerges, does it? You see these, what have we called them, hobs in the directed version. You see these high degree nodes which have like these many edges around them, because they have high degrees. Number 0 to begin with. Number 3 would be another one here. 61, I see 5, maybe 65. As opposed to the majority who only have 1 or 2 neighbors. So, where did we see this? The list of degrees here in K. Yeah, there's a list of node degrees. Node 0 has degree 45, node 3 has degree 23, node 5 has degree 22, node 12 has degree 9. And that's the nodes you see in here. 12. Where's 12? No, I don't know. Somewhere. And that's the degree histogram of this network. Displaying again the power law. There's many entries, 85 at the beginning, but then there are nodes of very high degree in comparison to the rest. Okay, as usual, the networks package has its own function for this. It's called configuration model. It works similar to ours, and we can feed the list of degrees into it and let the networks generate a graph from the same information, and that gives a similar picture but a different graph. What goes in is only the degrees of the nodes, not the actual structure of the graph. That's the configuration model. That's a way to generate, but with a prescribed power law, a graph that does look different from the random graphs we've generated before, doesn't it? So we look at this again using a slightly different approach known under many names, for example as preferential attachment, in the next lecture.